As described earlier, we only care about the total number of carriers, either electron or holes, but not where they are located in the energy band. That means we do not care about d of E, but just the total number of states. The first step to do simplifications is to assume the band is narrow so that all the states are sort of located near EC in the conduction band and EV in the valence band. Then we can define the equivalent density of states in the conduction band to be NC, and the equivalent density of states in the valence band to be NV. The value of NC sort of represents the total number of states if they are all located at EC. A similar definition is given for NV for the valence band that I do not want to repeat here. With NC and NV defined, we can look at the integral to calculate the numbers of carriers again. And the integrals just become the expression shown here. Starting from this point, I may sometimes just explain what is going on in the conduction band to save time. But you know that is similar for the valence band by considering holes instead of electrons. And you should be able to figure out by yourself what happens. The integral is removed because d of E becomes 0 besides at EC and EV after moving all the states to these energy levels. NC and NV are found to be given by the expression shown here, where Me and Mh are effective masses for electrons in the conduction band and holes in the valence band respectively. The values for silicon are 9.84 times 10 to the power minus 31 kg and 7.38 times 10 to the power minus 31 kg respectively. Some students often ask, how come there is an effective mass for holes as they are just empty spaces? It can be explained in mechanics that in order to push a bubble in water to move, you still require a force. And force is equal to mass times acceleration. Therefore, we can calculate effective mass of a bubble by the applied force divided by the acceleration. In the equation, h is the Planck constant equal to 6 times 63 times 10 to the power minus 34 joule-second. And k is the Boltzmann constant as explained it before. All these numbers are just constants that you can directly read out from tables. The only variable in the equation is the temperature T. That is, once you know the temperature, you know the values of NC and NV directly. As an engineer, I do not like to remember expressions, and we often remember some typical numbers. While NC and NV are temperature dependent, a good reference is room temperature, or 25 degrees Celsius. Taking this as a reference, we can calculate NC and NV for silicon at room temperature directly. And they are 2.8 times 10 to the power 19 per cm cube and 1.04 times 10 to the power 19 per cm cube respectively. These are important numbers that can be found in many tables.